Okay, so we're going to talk about moorings, and we're going to talk about what happens to moorings in the ocean. What you're looking at is a picture taken by my colleague Eduardo from the Rosenstiel School of Marine and Atmospheric Science. That big orange ball is a 51-inch diameter syntactic foam sphere, which holds an acoustic velocity measurement sensor. And it sits at the top of a very long mooring that is deployed in the Gulf Stream to measure the water currents and see what's going on in there. So the purpose of this talk is to give an overview of an investigation. We're really kind of just starting, but we got some really interesting results on what happens to moorings and mooring deflection, especially when what seems to be there's the effects of vortex-induced vibration that can amplify the drag. And yeah, so let's get on with it here. This mooring is called the MOCA 480C mooring. It's part of a series of moorings deployed across the Gulf Stream and across the entire Atlantic Ocean, really. And another thing that's really interesting about this is that the whole mooring is 5,000 meters long. So it's a long mooring. But there's a problem. Field data from this mooring. So there's also sensors along the span of the mooring measuring current flow all the way down to the seabed. Field data recovered from the mooring shows indications of a depth deflection of the mooring 500 meters vertically. And looking back at this and using velocity flows and trying to do calculations to figure out, what the mooring deflection should be is significantly underestimated by multiple different software tools that do this, including ProteusDS. So what do you do when you've got like vast underestimations of mooring deflection compared to reality? And that's what the focus of this talk is. So I'm going to cover a couple of aspects. First, I'm just going to give a little bit more of a background about DSA Ocean, the company I'm from, and our software ProteusDS. So you have a bit of context. Then we're going to go a tiny bit into a rabbit hole, not a big rabbit hole, but a little bit into calculating mooring deflection, what we're talking about with vortex-induced vibration, what does it mean, and then some comparisons with the calculation process and with the field data, and we'll have some more questions. Hopefully we'll have more than 5 minutes of questions, but you can ask questions throughout too. So just some quick background about DSA Ocean and ProteusDS. So who are we? We've been participating in marine beers a lot, so you probably are reasonably familiar with us, and hopefully if you work with us, you know a little bit more about it. But anyway, we started 16 years ago in 2006, and we're a spin-off from the University of Victoria. My colleague Dean Steinke and I started fresh out of grad school with lots of ideas and lots of enthusiasm about hydrodynamics, about simulation. We're working with this academic code to try to understand what happens to marine systems. We wanted to find a way to commercialize it. So hence we formed this consulting company to sort of make a vehicle for that. There's pictures of Dean and I from 3,000 years ago. Hilariously, Dean's working in his office at his kitchen table, and through the course of the pandemic, we went back to working on our kitchen tables, at least for a while, with how things are going. But anyway, today, Dean is our CEO, I'm our CTO, and we have our main office is in Victoria, but we do have a small presence in Halifax and a staff of 14 people, which kind of blows my mind a little bit about how things have changed over the years. And another kind of change through the course of the pandemic is that we've just been hiring more people remotely, like Bo in Newfoundland. It's provided a lot of advantages at finding the right people that are interested in this stuff and finding ways to make it work with the things that we do. So what does DSA Ocean do? There's two sides of this coin. There's ocean engineering services, and then we also develop software tools. In the ocean engineering services, a lot of it revolves around figuring out what happens to floating systems when there's wind, waves, and currents. We also do a little bit of work in establishing environmental conditions at the site, like what are the wind, waves, and currents? Because a lot of times we'll have customers and clients coming to us asking for a mooring design, but they have no idea what the conditions are like at the site. Then that's something we can help them with. And sometimes we do mooring site inspections. This happens in a lot of the aquaculture stuff that we do as well. And so the software tools, all of the academic nugget of code that we were working on 16 years ago, over many, many, many years has evolved into this what we call ProteusDS technology for this engineering physics solver for calculating what happens to floating stuff in wind, current, and waves. So we had this this core technology, but to really be successful and really engage with industry, we've been finding it crucial to make purpose-built software tools to really help our customers more clearly understand their problem, define their problem, and solve their problem with our software. And in the last few years, the biggest change for us has been these tools around oceanographic moorings, what we call ProteusDS Oceanographic, that includes a few extra tools for easily setting up an oceanographic mooring and going through the analysis process. And we are also developing other tools as well. And you know, Paul McCarley's in the meeting as well. He's one of our very capable software developers helping make all this happen too. So what kinds of floating systems do we look at? Over the many years we've been around, we've looked at things like floating tidal energy systems. This is a submerged tidal platform. Lots of interesting dynamics with the current flow and thrust from the turbines and the spread mooring, depending on the region we're at. And it's close enough to feel the dynamics from ocean waves as well, though it's not like a dynamic, it's not a dominating load. I mentioned fish farms a little bit. This is definitely a big part of what we do for services. Though we do have some ProteusDS users working on fish farms design. So what's important here is that there's a lot of components. It's computationally intensive, and bathymetry interaction with the mooring lines, and you need a lot of information to really understand what's happening in systems like this. Callum, you might appreciate this. This was a project we did 10 years ago. It's a cable ferry. This is actually the Bain Sound connector. This is kind of a unique sort of problem because it's both a ship motion analysis problem, but also kind of a mooring analysis problem. So this required analysis of the ferry traversing back and forth across the passage. And cable ferries have been around for a long time without needing, you know, this kind of detailed dynamic analysis. But the wrinkle here is that this is the longest cable ferry in the world, and there was a lot of concern about what happens as it traverses across the channel and what the loads might be like especially if there's a beam wind condition and waves on top of that. But by far, our biggest user base of ProteusDS is through our oceanographic tools and through oceanographic mooring design. And this kind of is a bit of a flavor on that. It affects some of the research that we do as well, and what I'm excited to talk about today on some of this mooring deflection stuff, which we'll get to in a minute. So again, who uses ProteusDS? A tremendous number of oceanographic organizations like Woods Hole, Scripps, and NOAA from Pacific Marine. I always forget what that stands for. Sorry, NOAA. Anyway, other NOAA offices like co-ops, and a lot of naval architects. Fuzz from Robert Allen. Robert Allen's a great customer of ours as well, and a number of aquaculture clients. So one of the main reasons we have so many oceanographic users is we have a parts library. We include a ton of commercially available floats and connectors and instruments that make it easy to put stuff together. So, and yeah, it's a really collaborative industry, and it's really exciting to see all kinds of technology come up, and it makes it easier for everyone to work together too. The interesting stuff. So we're going to talk about 3 parts: how to calculate mooring knockdown, and this is the first part. What do we mean by mooring knockdown exactly? So this little cartoon shows, if you look here, this is what a subsurface mooring might look like when there's no current. It just goes straight up, right? A little balloon on a string. But when there's a current, there's going to be some drag that's going to deflect the system laterally, right? And so the terminology that we use to explain what this difference in deflection is what the horizontal component is what we usually call excursion, and B, this vertical deflection from where it was originally is what we call the knockdown value. And there's also a tilt that happens, and this is going to change depending on how much you're along the mooring as well, both the knockdown and the tilt. But all of these are important deflection parameters to keep in mind. But we're going to talk basically only about knockdown this whole time. So why is knockdown important? Well, the really nice thing about it is it's really straightforward to compare with field data. And the reason it's easy to compare is because of pressure readings. So most stuff on the mooring, most of the instruments have pressure readings they're measuring. That correlates directly with depth. And so we can get readings back from sensors, from field deployments, and make a direct comparison to what our tools are telling us that the deflection should be and the predictions that we're making. But knockdown is also really important for other reasons. Most things have a pressure rating, right, including the flotation. If you exceed those depth ratings, like your flotation can fail and then the whole mooring can collapse, or your instruments can will fail as well. But there's also data quality implications. If your mooring is deflecting so much that you're so far off from where you think you are, that really adds a lot of uncertainty in what you're actually reading. The scientific value of what you're delivering is really compromised. So you have to be careful about that a little bit. So how do we calculate knockdown? ProteusDS is not the only tool that can do this. I mean, at the end of the day, it's math that's behind the code. Is a very common approach that's used, that's iterative, and you go through and evaluate a balance on the angle and the internal tension of the components with the external forces from drag and buoyancy and weight. So again, it's iterative, and it'll eventually settle on a deflection of the mooring in which the drag and buoyancy and weight all match up. And you're really, really curious, you can look more about this in the ProteusDS manual. So how accurate is it doing a calculation process like this? Well, sometimes you get really great agreement. Most of the time you get really good agreement. It's just that when you get some instances, especially in field data, where you see errors on the order of 400 meters, it's kind of concerning. And again, it's not just ProteusDS that's giving these errors. There's multiple other programs that people are using that give similar kinds of errors. So what's going on? I just made a really quick screenshot here to show a difference. This is a side view of the oceanographic mooring with that difference in 400 meters in knockdown. So that's to scale this 5,000 meter mooring, the underpredicted deflection, and then something that's much closer to what reality is. And again, if there is this error in 400 meters knockdown, there's 800 meters. There's almost a kilometer of horizontal excursion difference. So there's quite a big difference. So one thing that we found is that if you just increase the drag coefficient of the wire in the mooring to a value of 3, this is like almost tripling it, you get a knockdown error of 0. So that can't be the end of the story, though. Like, you can't just take a drag coefficient and multiply by a factor of 3 and walk away and call it a day, because there's too many problems that go along with that. So it's too simple. You know, how do you know when you should be applying this higher drag coefficient? And won't it be overestimating knockdown in a lot of circumstances as well? And what about the distribution of knockdown along the mooring line? Are you going to get some areas that have greater deflection than it should and lower? So one possibility for this greater knockdown is the potential for vortex-induced vibration. And we're going to talk a little bit more about that in a moment, but very generally, when a line is vibrating, strumming in the flow, intense vibration will increase the drag on the mooring line. So that's something we wanted to explore. So summarizing this first part, knockdown is the vertical deflection of the mooring. It's really easy to validate with field pressure readings. So it's a useful metric to make comparisons with. Calculating a static mooring deflection is relatively straightforward, but in some cases it is underpredicting based on these field data we're getting back in some extreme kind of scenarios. And it looks like there's some promise in looking at vortex-induced vibration and how it amplifies drag, but we have to figure out how to map the two of those together in an easy way that's very practical. And that's what part 2 is. How do we map some kind of estimate of vortex-induced vibration to this drag amplification? So the problem here is we know that vortex-induced vibration can amplify mooring drag, and we know that it's a missing component in most mooring models. So what do we do? Well, let's talk a little bit about what happens in the nature of vibrating lines and the nature of vortex-induced vibration. So in the nature of vibrating lines, what you're looking at in this image here, this is a vibrating line. It can be a guitar string. It's anything that's vibrating. It's just a string that's under tension that's vibrating. What you're looking at is the vibration envelope. So it's the amplitude. These are the nodes of vibration, the antinodes of vibration. It's vibrating in node 5 and this is the span of this line. This is the lateral deflection of the line, right? So the nice thing about this is that there's, for a line under tension, there's an infinite number of these vibration modes. They just increase by mode number 1, mode number 2, mode number 3. And you can kind of tell what mode it is by just how many little nodes there are here. So 1, 2, 3, 4, 5. Well, it's mode 5. Now, the other thing is, the higher the mode number, the more intense the vibration is, and the more humps there are in between here, right? So we're starting to get a picture that the more intense the vibration is, the more humps we'll see between them. And I'm going to call this wavelength, the distance between these two humps here, okay? The last thing I want to point out, I'm not telling you what the equation is, but there is there's an analytical equation for the natural frequency of vibration. It's a function of the line tension, the mass per unit length, and then the mode number, and so on. Now, let's talk about the nature of vortex shedding. Everything sheds vortices when there's a flow, okay? This is a picture of an island from space. The island is shedding vortices in a regular pattern that you can see that's visualized in the clouds. This is from Wikipedia. And I forget what island this is, but I mean, you get this asymmetric vortex shedding pattern, and that's what creates this lateral kind of oscillating flow. And of course, the island doesn't vibrate, and that's what we're going to talk about in a moment. But what's key to understand is that there is this vortex shedding effect that happens. It's very predictable. It's a function of your characteristic diameter. In this case, well, with the island, it's the diameter of the island, but for our mooring, it's going to be the mooring line diameter, right? And it's also a function of the flow speed. But the point is, everything sheds vortices, and it creates this undulating lateral force. So what happens with vortex-induced vibration is when the vortex shedding frequency locks on to one of the natural modes of vibration in the line, okay? So they have to line up, but when they do get close to each other, you start to get this vibration. And it's well known, there's lots of information in the literature that shows when this is happening, you get an amplified inline drag effect that happens on the system. But it's also self-limiting. So what I mean by that is, like, the worst case scenario, you would expect to see something like 2 or 3 times the drag, the regular drag of the mooring line. And also the vibration itself usually is limited at most to 1 diameter of the line. So you don't get some crazy kind of thing that's happening. It's self-limiting because if the line moves too much, it disrupts that vortex shedding effect, and then it stops shedding vortices. Then the flow reestablishes relative around the line, and then it starts shedding vortices again. It's sort of this, goes through this cycle. So how do we link these together, and how do we come up with a way to easily anticipate what that amplified drag is? So what we're going to do is we're going to make an assumption that we know what the flow is. That's an input into our problem. And when we know what the flow is, we know what the line diameter is, we know what the vortex shedding frequency is. So we're going to find, given some initial mooring tension and mass per unit length of that line, we're going to find the mode number that locally that lines up with that vortex shedding frequency. When we know the mode, we know what that distance is, that so-called wavelength here. And then the higher the wavelength, the shorter the wavelength is, the more intense the vibration is going to be, and the higher the drag amplification is going to be. Now, this is the only equation that's in the whole presentation, I swear. The reason I wanted to show this equation is not because I wanted to confuse anybody, but I wanted to highlight that this non-dimensionalized wavelength divided by the line diameter, its non-dimensional parameter, is only a function of the local tension of the mooring line, the local mass per unit length. So this would be like the wire rope, mass per unit length, for example, the local flow speed, and then there's this other non-dimensional parameter, the Struhal number, which happens to be a constant. So the point of this is that we can estimate what this wavelength number is with just the properties of the mooring by itself and some idea of what the flow is. Now, we do need to make a mapping for what this wavelength is to the drag coefficient, and it does require some calibration. And so we start with this initial fit for what maps this wavelength to the drag amplification. And I have this mapping here Okay, it's a very simple mapping, and I've used several cases to help sort of go back and forth and make a quick adjustment with this. What you're looking at the horizontal axis is this non-dimensional wavelength, and then this vertical axis here is the drag amplification. So worst case, we're getting 3 times drag amplification, and then if it goes too tight, well, there's no drag amplification. At an upper limit, there's not really a significant vibration, so there's no drag amplification. So I know this is a lot of numbers, and conceptually it's like, what is he talking about with this wavelength? So if we take this non-dimensional number of around 300 and this other limit, this non-dimensional number around 10,000, and look at an example, typical oceanographic wire might be something like 6 millimeters diameter. So what we're really saying is if the line vibration is something like less than 2 meters or less, well, we're going to say that's not really going to be able to vibrate. The jacket, you know, the plastic material over the rope is preventing it from vibrating. There's a bit of bending stiffness there. There's some damping that, you know, realistically it just can't make a tighter and tighter vibration in the line. I don't think that would really exist. And on the other end, you know, this so-called 10,000, you know, non-dimensional wavelength is a 60-meter length of this vibration. It's just not that intense of a line of a vibration, so it's not really going to have a lot of vibration. And I'm non-dimensionalizing it because that way I can apply the same curve to, you know, 9 millimeter wire rope or 10 millimeter wire rope or fiber rope with slightly different diameters. It's just a way of exchanging that data across different problems really easily. So are we actually calculating the vibration response of the mooring line? No. We're just trying to play with boundaries of this problem and try to make a case for when the right time would be to apply an amplification of drag. I just want to make sure that that's clear. So in summary, everything sheds vortices, right? There's always vortex shedding happening when there's this relative flow that's happening. The real question here is there some intense vibration or not? And that's what this whole mapping process is all about. We know that VIV, when it is vibrating intensely, you can get this drag amplification, in the worst case 2 to 3 times. And this process that we've outlined gives us a systematic way to calculate what that might be, just given basic mooring parameters from the basic design. But again, we do need some calibration, and then we're going to go through and look at some actual data from several different mooring deployments and see what happens to when we apply this approach and see what happens to the mooring deflection. So the whole point is here, we want to see some amplification of the drag. We want it to deflect more when we see field data when it's deflecting more, but we don't want it to be over predicting too much, especially when we're not expecting to see a lot of deflection in moorings. So we have 3 cases to look at. There's all of these moorings are deployed in high flow environments that we'll talk a little bit more about. So first we'll look at the DWEAB mooring. This is a NOAA co-ops mooring. DWEAB stands for deep water acoustic buoy. So yeah, it's measuring currents and it's 325 meters long. I forget what DWEAB stands for. Sorry about that. So this is in the Gulf Stream off the east coast of the U.S. and it uses this low drag elliptical buoy. You can see a picture of it there. That should be during recovery, I think. The flow speeds in this region were reaching 2 meters per second. And there's lots of data on the knockdown of this actual mooring. So let's look at some results here. I know there's a lot of numbers here. The flow speed for the whole water column, we had some lower end speeds of 1 meter per second, medium of 1.5 meters per second, and 2 meters per second. The actual knockdown values of the top float, so that's how much vertical deflection was there really observed, was 10, 28, and 48 meters. Now, if you just apply a drag coefficient of 3 on the mooring line, it's a little bit better and then starting to overpredict. And then in the worst case flow, you're getting like 82 meters knockdown. I mean, like it's far in excess of what it should be. And then when we look at some comparison of what we're getting out of ProteusDS when we apply this algorithm with the amplified drag and then without any amplification of drag, we're getting a little bit more, but I'm pleased to see not too much more deflection because there shouldn't be. So what this is really telling us is that it's picking up that it's outside of that really heavy VIV kind of region based on the data that we set up, and we're seeing a little bit of drag amplification, but not too much. So I was happy to see that. But that said, we could be doing a bit more at lower speeds. So there's some adjustments we could probably look at doing. So we have another mooring to look at. This mooring is 4,200 meters long, and it's in the East Australia current. So this is Australia, and then we have this very interesting I think it's an eastern boundary current along the coast of the continent that makes all kinds of very complicated flow patterns. This EAC, East Australia current mooring, is in an array just off the coast of Brisbane. And the one that we looked at was one of the ones with the most significant knockdown. Now, this is not my ideal data set because we're looking at the 95th percentile current profile and 95th percentile mooring deflection. I prefer to look at the actual current profile, but it was some data that we had access to. So we looked at, I know there's a lot of details here, but what's key is there's a couple of ADCP floats, acoustic Doppler. This is like the primary flotation in the mooring where there's some velocity sensors. So we compared a couple of points along the mooring. And this is the current profile, the sort of like substantial current profile you see with quite a lot of flow in the upper region, but it does taper off. This plot, I've tried to superimpose things to show the knockdown at the top of the mooring, about 2% along the mooring, 15% along the mooring, and 50% along the mooring. We have field data in dark, so this is the measured data. And then in red, we have a ProteusDS result with no VIV amplification, and then with VIV amplification. And the moral of the story in looking at this is like mostly we see a closer matchup with the data from the field deployment, even though it is 95th percentile. I have, since making this presentation, I have more data from Cyro, who deploys this mooring array with much closer current profiles to the actual mooring deployments. Just haven't had time to look at it and do another comparison. Nevertheless, it's promising. And yeah, what was key is looking at the knockdown distribution as well along the mooring. It's encouraging to see mostly we're getting better results. Now, this is the really important one, the M480C mooring. This is the one that we talked about at the beginning. So how did we do in comparison? So what I've got is, again, depth measurements from the top float and from several sensors all the way along the span that are also measuring velocity. And so we have many points to compare the knockdown with along the span of the mooring. And we also have 6 current profiles. 3 of the sample current profiles were associated with this very large significant mooring deflection. And then we also have 3 sample profiles with a very large surface current component, but not really much associated mooring knockdown to speak of. So we wanted, this is great because we can see, do we get deflections we hope to see? And also we don't want to see too much over prediction of deflection in the lower speeds. So this is the worst case scenario in current profile 4. Remember, this mooring is 5,000 meters long. The field data is in dark, this dark color at the top, and we're getting very close to 500 meters deflection here. Without VIV amplification, the results are, around kind of 100 meters calculated deflection. But when we turn on this VIV amplification algorithm, we're getting amplifications that are, it's actually not quite getting, even still, not quite getting to what the field values are, but it's substantially closer to what's measured. And the distribution kind of follows along the span of the mooring quite well also. Here's another example of a severe scenario. And in this case, we have worst case measured mooring knockdowns of 300 meters, again, under predicting by several hundred meters. And in this case, with VIV amplification on, we're like over predicting a little bit, but it's still generally getting much closer to the real results. This is another problematic current profile measured at a different time. And again, you're seeing kind of similar results. Field data showing something a little bit more than 300 meters of knockdown, under predicting without any amplification turned on, but then we're getting much closer, and then under predicting by a little bit when VIV amplification is on. So now we're looking at a current profile results where there's like a pretty high current at the surface, 1 meter per second, and even some significant current in the lower portion of the mooring, but there wasn't really much mooring deflection detected. In this case, what I was worried about is seeing too much mooring deflection. So the field data is, kind of a little bit more than 100 meters. We're under predicting without VIV amplification, and then over predicting when it's turned on. But still, I've kept the scale here the same to remember the context of the worst case scenario profile. Here's another example. This current profile, there's not a lot going on. In fact, without VIV amplification, it's matching up a little bit better than with the amplification on. And then again, there's another example here where there's not, almost 1 meter per second at the surface, not a lot of going on with mooring deflection, and we're kind of over predicting a little bit. But again, you got to keep that error in context with the worst case scenarios that we saw earlier. So in summary, it's tricky because we see a lot of promise in what this can do in helping kind of help eliminate some error and uncertainty. It certainly seems like we're getting some promising results when there seems like there is some strong potential vortex shedding effects and vortex induced vibration. But there's also, in some cases, some overprediction in lower current profiles. So what do we do now? I have more data. I have more data from some of our colleagues as well. I want to explore a better, more sophisticated curve to map the vibration effect and the drag, so we can kind of tweak, how well it fits. But that takes time to do, of course. And still, I'm very pleased with what we have. There's other things as well. I mentioned the Struhal number is a constant, but in some lower flows, the Struhal number starts to change in known ways, but we just have to account for that and things like that. But yeah, one other big factor is it's really cool to see all this from an analysis perspective, but what's really important is trying to understand how we can design better moorings, knowing that we have this capability, because being able to anticipate the amplified drag from VIV is good, but it also kind of depends on the current profile. And if you don't know the nature of the current profile ahead of time, it makes it a kind of a challenge. So there's some ongoing discussion with that. That's kind of a challenge. I have some ideas on that, but that's something we can talk about either maybe in this meeting or maybe one-on-one in other meetings as well. Yeah, so I just want to make some acknowledgements. A lot of the data was made available by my colleagues at the Rosenstiel School and as part of the Rapid MOCA program. And this is a collaboration with some organizations in the UK as well. And I also want to acknowledge my colleagues from CSIRO in Australia and IMOS, which has lots of freely available oceanographic data from flow and moorings as well. So, and yeah, I just, again, wanted to say thank you to my colleagues at the Rosenstiel School, Bill, Guy, Eduardo, and Pete Jansen for being so collaborative, and from NOAA Co-ops, Laura and Robert, really collaborative, really willing to share data and enthusiastic about finding new ways of doing things. I use this slide a lot in the presentations that we do. If you want to go fast, well, go alone. But if you really want to go far, I mean, no one can be an expert in everything. And we really value and look for ways to collaborate with other people and share information to find new ways of doing things. So that's the presentation.
Thank you so much, Ryan. That was amazing.
Yeah.
Very clear. There, you made me feel smarter at various points along the way. So,
okay. Great.
Question period. Anyone have any questions? Maybe I've got one just to kick us off here.
Sure.
I'm not sure if I followed. Okay, so you've done this analysis. This sounds like it could have a pretty big impact on mooring design. What do you do if you feel like you've triggered one of your thresholds? Is it just a question of making that top float bigger, or?
Good question. So I don't want to go back to that equation that I showed. I know that showing equations makes it kind of disorienting a little bit to look at, but that really is the key to seeing what you can do about the mooring design. And so you know that the tension and you know the mass per unit length are two different things you can play with to see about how you disrupt the design. And I think about things like, okay, rather than having one giant float at the top and one uniform line all the way along the bottom, could you have two floats along the span, you know, one in the middle and one on the top? And then what would happen if you had, you know, wire rope through 500 meters of the mooring and fiber rope in another 500 meters of the mooring, which fiber rope is extremely light. So the mass per unit length is totally different. And then wire rope again. And I know that it's easy for me to say these things, and I'm looking at Noah Lawrence sweating and getting worried when I start saying things. Logistically, now you're making things way more complicated. Now it's way more difficult to put the mooring together on the deck of a ship. It's way more costly to use fiber rope. Okay. But the point is, these are some trade-offs that you can try to make when you have the tools to understand how they make a difference. So yeah, that's what I would do. That's what I want to do. I just don't have the time to explore that. What I would next do is I would take the Mocha M480C mooring with the problematic profiles I have. I would throw in two floats, and then I would see what happens with what this algorithm says and what the resulting deflection would be, to see how that change, that significant change in tension profile along the span makes a difference. And also potentially playing with the line, like alternating mass per unit lengths that are a little bit different, you know, and see what happens. I think we have a question from John Zand.
Yep.
Fire away, John.
Right on. I was kind of curious as far as, like, are you able to compare the magnitude of vortex induced vibration on, like, your floats compared to your cable? Like, is there like a magnitude there?
That's a really good question, and I was not expecting someone to ask that, but it's perfect. In no way have I done anything with the vortex shedding on the floats, and it would be different because they have a big different diameter. I think it's actually really important to look at the vortex shedding on the floats, because that creates a totally different frequency, and it's definitely possible that if you have a mooring designed the wrong way, that could line up with the pendulum natural frequency of the mooring, for example, which is definitely possible, and that kind of thing happens. So yeah, that doesn't affect this particular problem because the mooring is 5,000 meters long. I don't think that the vortex shedding on the moor at the 51-inch float at the top would really be. It might create a little bit of like localized vibration, but it's not enough to create something so significant across the entire span of the mooring in this particular scenario. But yeah, that would definitely, that's something I do want to look at in the future, but that becomes a future thing to look at. So yeah, but good question. Yeah. Looks like Callum, you have a question?
I do, yeah. Super impressed by the work you're doing here, and I do have an appreciation for the cable ferry aspect you raised. I've attempted to look into that myself, and I know it's a very challenging thing. So I guess my question is, like, what are the real world implications of over or under predicting knockdown? So what does this mean for your clients?
Right. Yeah. So the information that's being recorded by all of the instruments along the span. I mean, first and foremost, just to reinforce, it's an engineering problem. If your mooring is deflecting more than you think it's going to, like that 51-inch float has a depth rating. If the depth ratings exceed it may collapse, and the whole mooring may sink to the seafloor. You've lost, like, a day rate for a ship to go out there and get it is, you know, $10,000 a day, even more. Like, there's huge implications for going out. You've lost all the instruments. One ADCP maybe $50,000 as well. Like, all this equipment is hundreds of thousands of dollars. You don't want to lose your equipment if you can help it. Now, for the data quality implications, I can wave my arms about that a little bit, but not being a marine scientist, it's hard for me to kind of get into that level of detail. But the measurements made by these systems are usually inputs into numerical models on greater ocean circulation patterns as well. So maybe there's not necessarily as much of a problem if your mooring is off by a kilometer when you look at kilometric scales of flows, but it starts to introduce uncertainty. And if you're starting to introduce uncertainty on like the mass flow of water through the Gulf Stream, that's going to ripple on in errors through, you know, how all these ocean circulation models work, which affects, you know, weather predictions and weather weather modeling as well, and a lot of other stuff. So yeah, but this is me waving my arms, and yeah, there's other people better qualified to understand the data quality implications. Now I see Noah Lawrence has his hand raised, and he may actually be a good person to provide some additional commentary on this. Sorry about that, Noah, but yeah, I'd like to hear your question first, though.
Yeah, well, maybe I'll just comment on our issues with, you know, mooring depth, particularly when we're looking at ADCP moorings or things where we're looking at surface currents and things, and also when we're looking at acoustics, when we have hydrophones and things, and you want to make sure you're in the sound channel and things like that. For, you know, acoustic moorings, we really need to be, you know, maybe in 5,000 meters, we want to be within like 10 meters or so of our target depth. So pretty precise, you know, and maybe 20, 30 meters sometimes for the hydrophones. It depends on what, you know, the acoustic kind of layer is at that point. But yeah, so you do have to be pretty precise on these. And if you're outside of that, then you have data implications where you either miss, you know, your surface, or you don't go deep enough kind of in terms of what you're looking for. You also worry about, you know, being knocked over too much and having too much, you know, angle on things like ADCPs and things like that. My question was, you know, we've looked a lot at VIV, not so much from a modeling standpoint, but we've spent a lot of time playing with different ways of reducing VIV because it's a real big problem for us in these deep ocean moorings. What data would be useful to you to improve, you know, to make improvements on, you know, the ability to predict VIV, to model it? I mean, what data would, you know, if you had like the ultimate data set that would answer kind of your question on, you know, and help kind of push the science forward on this, what would it be?
Yeah, well, I mean, it's like the data that I showed and more data just like it, you know, I've got the mooring schematic, so I have all the mechanical details, the mass, diameter of the line, all that stuff is good. I really need to know the current profile when the mooring deflected at that crazy depth of whatever it deflected at. So we can then use that and say, okay, we have a good understanding of what the flow conditions were like at the mooring when it was doing this thing. That feeds directly back into like how we can, you know, make that calibration curve and refine it a little bit. Like what I've done is just scratch the surface. Like, you know, this is what I could do in like 2 afternoons kind of thing. And, you know, it's like very, very basic scratching the surface. It gets hard to go through the data and just dig out the data when you have that current profile at that exact moment. And if I get like a, you know, 200 gigabyte data set where I have to dig it out myself, like that takes a lot of time to find the exact numbers and everything, right? So as well. Yeah, that's what I would say right now. I've got some really interesting data from CSIRO as well on the Arctic circumpolar current. So for those of you that don't know, and I only learned about this recently, the Arctic circumpolar current is like, it's kind of like the Gulf Stream, but it's circling around and around in the middle of the ocean at the pole, at the South Pole. And they've deployed moorings there and make all kinds of measurements, and it has big implications for understanding what's happening on our planet too, and also big mooring deflections as well. So I've got more data, and I want more data. I'll take all the data, you know, but it just takes time to go through it all. This leads me into limitations in what we're doing right now. So right now we're looking at moorings that are in very big, you know, ocean depths. Current profile variation is like, you know, we'll see 2 kilometers or 1 kilometer of this slab of flow in the Gulf Stream. So something that makes me a little bit worried is like, well, if you've got some fine detail in that variation, what's going to happen with this algorithm? Is it going to pick up on that? Are you missing something, right? I don't know. When I look at the DWEAB mooring that we looked at, that's in only 300 meters water depth. Inclination of the mooring becomes a factor because a mooring that's completely horizontal, it's not going to shed vortices. So that's another thing. That's another bit of a wrinkle, a big curveball. But that would be something I would be interested as well. Like, well, do we have more data where there's moorings that do have this inclination effect more, as well, But yeah, I sort of feel like there might be a bit of diminishing returns on more full ocean depth moorings. Like, how many moorings do we need to look at before we're happy with our curve, right? And I guess certainly we'd want to know if, like, is it totally off, or overestimating when it shouldn't be. But I think that's an engineering judgment. You can flip the switch and see what happens, and then make a judgment call on whether or not it's serious, right? Which leads me to another thing that I would do. If I don't have any information on the current profile, what do you do? How do you make a better mooring design? And I kind of had the thought that you could do something like just put in a uniform current profile, even if it's full ocean depth, which is not realistic. But if you design a mooring with 2 floats and you have that tension difference, and you compare relative to a simple design, that might tell you which one is a bit more resilient and has less knockdown, compared to the other one. So even if you don't know what the current profile is, there might be some things you can do to kind of play with, not in terms of finding an absolute, number for knockdown, but gauging performance in, resilience of this mooring design to resist drag amplification, if you have something like this to help you. Does that make sense?
Oh yeah. Yeah,
Okay.
very cool.
Cool. Yeah, so that your comment on tilt angle, Noah, reminded me of an important part of data quality. So back to Callum, your question on data quality, an acoustic Doppler current profiler. Do you know what an ADCP is? You know what I'm talking about? Vaguely? Yeah, so I mean, it's using sound to measure current profile over a distance, right? And potentially a kilometer of distance. Any ADCP will significantly degrade in its ability to measure currents if it tilts more than 15 degrees. So if the mooring, when it has severe knockdown, it's also going to tilt. If the greater the tilt, the greater the degradation is going to be. And so now you just have a big uncertainty on what you're actually measuring. And unfortunately, those things are going to happen under severe current profiles. So you're missing the most interesting, most severe, currents that you really want to know accurately, right? I mean, it's like, telling a ship captain, like, wow, the sea's pretty bad out there. And you're like, well, I really need to know what the sea state is. I don't know, it's pretty bad. But when it's calm, I can tell you it's 1 foot chop, 1.1 feet chop, no problem. 100% sure. It's like, I don't need to know that. I need to know the most severe conditions, right? Accurately, yeah. Evan has had his hand up forever, so it's probably his arm's going to fall off. Evan, do you have a question still?
Digital hands don't get tired.
Yeah.
Yeah, so mine kind of takes it back to, my question takes it back to one of the first points you brought up was, VIV in general. This is the first I've heard of it, but of all the possible hydrodynamic effects that could have been causing that increased knockdown, how did you guys narrow into deciding that VIV was the culprit? And did you take any perhaps wrong turns in getting there?
I would say my life has been like one wrong turn in VIV after another. The reason that I was thinking about that, I've basically been thinking about this since my master's degree. My master's degree under Brad Buckham, way back in 2005, was on vortex-induced vibration of a riser in the ocean. And that was very painful and confusing. There's a lot of crying, but I got my degree and I'm out of there. I never want to touch VIV again, right? But I still remember all of the characteristics of it. Like there's drag amplification, all of these things, right? And so over the years, I've checked in on VIV research every once in a while. And like it's still extremely complicated, a very nonlinear phenomenon, really difficult to predict. People doing tank experiments and CFD and taking a long time to figure out what's going on. I just kind of happened to be at the right time at the right place, collecting information, working with people in oceanographic moorings. I hear stories from Noah Lawrence and other people like that, where, oh yeah, we're trying to suppress VIV, trying to figure out what's going on, and having a bit of time and place to play with an algorithm like this, with that historical kind of perspective, revealed this this algorithm, this approach to use. So I wouldn't say it was like, we didn't do a systematic review of a whole bunch of different things. It's just something that we've been aware of for a long time. And through my own personal experience and knowledge, like I had the ability to kind of play with something and come up with this algorithm. And then it kind of works. So, I mean, it seems to work. I don't know. I mean, that's engineering, right? You try to make a physical basis for things, and you know, build up on top of that, and then try to break it, you know, with more complicated stuff on top of it. Does that kind of answer your question? Like, I don't know what else it could be. I have no idea what else it could possibly be. I mean, I don't think it's something like Reynolds number variation on the drag coefficient. It's not that, because the flow speeds are not changing that much. The flow speeds are all kind of the same. It's just like a different combination in the water column. And so then it's like, you know, what else have you got to play with, right? What else makes the drag coefficient change? Well, people all know that there is some kind of vortex shedding thing happening. You see wear on the shackles when they come back, from as if there's been like cyclical stuff happening, you know, as well. So people have reasons to believe that there are like vortex shedding happening, you know, as well.
Sweet. Sounds good. And I mean, ultimately you nailed it. If it's predictive, who cares, right?
Yeah, a little bit, you know, kind of, sort of, you know, you hope. You don't feel bad, you know, I mean, that's probably a good thing. Yeah, I think, you know, Dustin was mentioning we're actually getting close to the end of our hour here. So maybe if there's one more question, we might try to cover that. I don't want to keep everyone too long.
Maybe we'll call it there.
Yep, no, sounds good to me.
Ryan, thanks so much. You've been co-hosting for years now, and so it's great to hear a little bit about what's going on at DSA.
Yeah, no, I was glad to talk more about it, and yeah, really appreciate the discussion. Really great questions. Great to see some new people coming out as well. So yeah.
Thanks a lot, everyone, and I guess we will hopefully see you guys all next month.
All right, take care, everybody.
Yep, thank you.
Thanks all.
Excellent presentation.
Thanks, Ryan.
Way beyond my math capability, but you did an awesome job of explaining a concept. So well done. Appreciated.
Thanks, Buzz.
I know. See you again, guys.
Thank you, everyone.
Bye,
Bye-bye.
Buzz.